So welcome back everyone to the Open World Lifelong Learning course. We're in week 6 today, so we're almost halfway through our entire course. And today we're actually going to also wrap up a major block of the course, basically the first half, by talking about what I'll vaguely refer to as dynamic or modular neural architectures. I'm putting the neural in here specifically because although conceptually, we'll be talking just about architectures like machine learning architectures that are extendable. We'll be primarily taking a look at neural architectures because it's already a big chunk of information in itself. So I've tried to not overload this. So recall where we are in the lecture overall. We've talked about first of all, a motivation introduction, and then we've spent a little bit of time on transfer learning in terms of transferring knowledge to a new task without so much caring about our source or our initial tasks. And then we've talked about the version where we actually also care about keeping our knowledge of previous tasks. So how to avoid essentially forgetting, mainly catastrophic forgetting. We've then seen these various paradigms for what is referred to as continual learning in how to avoid catastrophic forgetting, where we've talked about the idea of regularization and knowledge distillation, illustration B in this diagram. And then we've continued on with rehearsal strategies, first in terms of rehearsal on real data, then in terms of pseudo-rehearsal with a generative model in this D illustration, in this D panel of this figure. Now, we've deliberately skipped talking about C when we first encountered this diagram, and C is all about essentially putting on expert heads or expert models on top of already existing model pods, adding units to a model, all these sorts of questions. So basically, as the task complexity rises, so does the complexity or the amount of parameters of our model. We've deliberately not talked about this initially because we've done a small detour in terms of active learning first, where the idea in active learning was to talk about how to query data next, so what comes next. And so today we're going to actually talk about this C panel and talk about the idea of adding parameters, adding modules to our already existing architecture, just because it's now a good time to talk about this after having visited active learning. And the reason for this is, let's take a look at some quotes of how sort of architectures are presented in the context of continual learning and in the context of catastrophic forgetting specifically. So in this rather, by now, fairly old quote that's almost 30 years old in one of the earlier works, it says, catastrophic forgetting is a direct consequence of the overlap of distributed representations and can be reduced by reducing this overlap. So basically, it's talking about the fact that at least in neural networks and a lot of other machine learning models, but particularly in neural networks, the representations overlap. So there's no clear distinction in one parameter belongs to one specific concept or represents one specific concepts, but there is a form of entanglement of the information across the parameters. And so that's the reason why we've also talked about regularization, where the idea was maybe to find a subset of parameters that we could constrain to keep for all the tasks and a new set of parameters to go into further tasks. But quite crucially, coming up with the second quote, it's also a question of like stability versus plasticity, right? We've had this quote of the stability versus plasticity dilemma, where there's a limit to how far we can maybe constrain what we already have and how far we can let new parameters drift if there is such an overlap. And in a very extreme scenario that we could maybe briefly hypothesize as the ideal scenario, we could think that we may just want representations that are completely particular to one concept and other representations that are completely particular to another concept. But then what we need to realize, I think is very nicely expressed in this quote, is the motivation where we started entangling parameters in the first place. And that is, very local representations will not exhibit catastrophic forgetting because there's little interaction among representations. However, a lookup table lacks the all-important ability to generalize. So what this quote is basically saying that you can't really have both at the same time. So if you want representations that are particular to one concept, then it's also harder to leverage joint knowledge for multiple concepts at the same time. Whereas on this perspective, it would basically be a lookup table. It's very computationally infeasible. So there's an advantage to actually having representations be entangled, be shared, but there's also the disadvantage that we may have to deal with forgetting them. So we'll talk about dynamic models then today, where the idea is that maybe we can have some sort of mix. Maybe we can have entangled parameters that do represent a task, but then we can also maybe add parameters over time as the task differs, so there's only parts that are shared. And of course, it may initially be very intuitive to think about this, but I also want to right away from the start emphasize that whatever we're going to talk about today, independently of how it's perhaps displayed in one or the other literature paper, it's not only about catastrophic forgetting. So my critique in that sense that I've just voiced stems a little bit from the fact that sometimes if you look at these reviews, especially the one I've linked before, there is an advocacy for changing architectures over time as a solution to catastrophic forgetting. And while certainly this is true, I also think that dynamic architectures or architectures that have suitable amounts of capacity that can change over time are a essential concept of machine learning itself. And so for that purpose, recall this plot that we've seen in the very first lecture as an example of what is expressed in the machine learning introductory courses in the introductory books, here in this case in the deep learning book. And what you can see here is that as the number of training examples on the x-axis scales, as our datasets grow more complex, so should the optimal or the ideal capacity of the model that we construct. Here it's again on the example of this polynomial that we've had, but basically as we grow ever more complex in tasks, we also require a different complexity in the model. And that is not just a thing against catastrophic forgetting, that is also a thing that just is required in order for us to encode new knowledge. So I don't have it here as a slide, but if you recall very briefly, we've had this illustration now twice in the past lectures where there was an example of a neural network that was trying to learn permutations online. And as the model had very little parameters, at some point it could no longer encode new knowledge, whereas a model that had a lot of parameters was doing a much better job in just acquiring new information. And so whenever we now talk about catastrophic forgetting from a perspective of changing the model architecture, adding parameters over time, we also need to take into account this perspective of not just catastrophic forgetting, but also about being able to encode new knowledge. And so with that said, as an intro, I want to transition to maybe the two common ways to think about modular architectures or dynamic architectures, whatever you may want to call it. You can also see the reason why I've had such a long introduction right now. And it's because one of the, let's say, at least two commonly advocated ways to think about modular architectures and catastrophic forgetting is by going and taking an implicit route, or what I call implicit here, because we'll be assuming that we start with a model that's extremely overparameterized, and then retrospectively maybe try to create specific submodules in there. So it's a little bit like what we've already started in the elastic weight consolidation and the synaptic intelligence idea, that we'll start with a model that is so large that we can in fact identify parameters that are only responsible for one task, but we'll still have so many parameters left that are right now redundant that we can just create like sub-routes, sub-paths of a model that is now responsible for a new task. I'm calling this implicit here because it's implicit in a sense of you start with a very large model and then try to create these submodules, versus what I refer to as explicit here is perhaps, at least to me, the more intuitive approach, where you would just, as you go on the fly, add the actual parameters, add the actual capacity over time. So if you start with a very simple task, you also start with a very small model. And if you figure out that the task gets more complex over time, or that there's a new task that's more complex, you simply add parameters or capacity. Now, of course, I'm saying simply here, but there's an absolutely valid reason, which we'll see in a second, of why this implicit sort of perspective exists. Because although the explicit one, at least again to me, is more intuitive, it's also not as easy and not as simple to implement for sure. So let us start with the implicit perspective and also start with a fairly simple example on the next slide where we can understand a little bit of what we desire, what we may want if we frame catastrophic forgetting from this perspective. Now, for that purpose, recall very briefly again that we can see this maybe as a combination of regularization and over-parameterization in the sense of that we want to start with a very large model. We want to have a lot of parameters, and then we may want to do something like either sparsify the parameters, so sparsify in the sense of really the activation patterns that we observe are closer to 0 and 1 rather than completely distributed, or we want to maybe just identify the subset of important parameters, the subset of important connections in the neural network, and create like sub-modules within a larger set. And so one of the older ideas that has voiced this in a somewhat intuitive way is the concept of activation sharpening. So the concept of activation sharpening also goes under the premise of semi-distributed representations. And what it essentially advocates is rather than having all the representations in a neural network and trying to just disseminate information through all of the nodes, we want to maybe constrain our neural network to only produce high activations for specific concepts in a maximum number of, for example, k amount of nodes. And for all the remaining activations, we'll maybe not want to sparsify them completely in the sense of setting them to 0 so they don't activate because we'll lose then some of the representations, but we'll maybe want to put less emphasis on them. So we want to decrease the activations here. So in this specific example, it's suggested that we could measure the overlap as a sum of the smaller activations, the so-called like shared activations, as a measure of the interference for how much activations overlap. So what we can see this in this example of the two vectors that I've put here in an example of 4 hidden units, where you just have the calculation of an activation overlap here. So what you would do is you would go through both of these vectors. You would pick the smaller of the two activation numbers. So for the first entry, it's 0.2 because they're both equal. And the second entry, it's actually 0 because it's the smaller of the two. Then it's 0.9, and then it's 0.1. You'd sum these. You'd normalize according to the length of the vector, the length of the amount of your hidden units, and you'd get something that is referred to as activation overlap here, which corresponds to 30% in this example. Now, the non-interfering example is also illustrated here, where it's quite obvious that it has 0 overlap because you'll just be adding zeros in every element and you'll divide by 4, which doesn't matter. So it's still going to be 0 overlap. But of course, keep in mind that we've just said that this extreme example is respectively a lookup table, especially if we only have one hidden layer, like we'll assume so now. The key idea is then really to use this in optimization, and I've just screenshotted the proposed algorithm in a very verbose form on this slide. But all it's really saying, without reading out all the details, is that we'll just regularly perform our forward computation, so our computation of the functions in a neural network, and our backward computation, so the computation of the gradients in our neural network. But in addition, in each step, we'll now have this extra idea of sharpening the activations by moving up the activation of the k nodes, the k largest nodes, and moving all the other activations down, calculate the differences to the old activation, and respectively modify the weights such that it works out. We can see this maybe more intuitively in a visual example of what this would look like in terms of actually visualizing the activations, and it's illustrated on this slide here, where we see the effect of this activation sharpening method on a hidden layer, a single hidden layer of a neural network with respect to how it looks like in the standard case, which is on the very left. So again, you can see here that in the 1, 2, 3, 4, 5, 6, 7, 8 nodes that you have, you can see that each of them sort of activates for the specific input, which is expected, but it's also maybe slightly undesirable in the sense of that it's now completely entangled and you'd have some form of catastrophic forgetting once you start trying to optimize the weights that lead to this activation towards a different task. And in the sharpening examples here, you actually see a quite different pattern where in the one node sharpening, you see that only one activation really peaks quite heavily and the others are pushed down. And in the two node sharpening, you could see that two activations are peaking, whereas the other ones are pushed down again. And so the idea is maybe that you can find some sort of a trade-off in having a certain amount of activations be large and the others be a little bit smaller, so that the idea is that if you lose some of the smaller activations when you later start overwriting them with a new task, with a new concept, you're also forgetting less, or at least you're not maybe forgetting catastrophically. We can take a look at this in another example, which becomes maybe more visually clear if we start taking a look at how this has recently, or more or less recently, been implemented in a deep neural network variant. So here you see a deep neural network trained on some reinforcement learning tasks on Atari games specifically with two hidden layers. And you start with, in this panel 1, again, an overparameterized network. It has a lot of weights, it has a lot of connections, and of course you start by randomly initializing the weights. So this is what you'll see in this illustration with a lot of purplish connections, some of them slightly heavier than others, or slightly more shaded than others in this visual diagram. And you could play the same game as activation sharpening in the sense of you want to constrain now, when you start learning a task, the number of activations or the number of connections that really get activated heavily for a particular task at a time. And in this case, in panel 2 of these 9 panels on the center left, you can see that the choice here seems to have been to limit the activations or the large activations to 5 units. So you can see in the first layer, there are 5 units that get activated, the rest sort of falls into the background. And the second layer, you again have 5 units that get quite heavily activated. You can then see that at the step of 3, where you start converging, this is even, actually it's only 4, so my guess of 5 was wrong. I guess you're trying to push it into 4, but initially it's not as, you don't really achieve this. But eventually, actually, it's pushing it into 4 connections at maximum, and you'll find out that this then converges on the Pong idea on the Pong game to a potentially satisfactory level. Now, once you have this converged, you would then maybe think about adding a new task to it, which here in this case is the alien game. And the alien game now, it has a lot of choices where to use the remaining capacity of the neural network without explicitly interfering with the connections that have already been established to be very important for Pong. We can see this in these illustrations of 5 and 6 and 7 and so on, with the red lines that are illustrated here, where the important thing is to see that the newly formed lines are not overlapped with the ones that we've already established. So actually here the red ones, sorry, I've said it the wrong way around. The red ones are the ones that are constrained with respect to the Pong. It's the same ones we've had in panels 3 and 4. And we can have various options in a light shade of green and then orange here that are potentially not so easy to distinguish to be trainable for alien. And then again, we're going to get a subset of a maximum number of activation patterns of weights that are responsible for this specific task that occupy a little bit more of this completely over-parameterized model. And then at 9, we'll maybe add another third task that's not completely illustrated here, where you can have the blue options as all the remaining choices that you could now have as suitable choices to encode in your task. We can see this similarly, but from a different angle, rather than taking a look at all these connections, from one of the approaches we've already had in the past, which is the variational autoencoder, where one of the ideas here was that, again, we have an encoder and a decoder that's extremely heavily parameterized, meaning there are a lot of parameters that can transform our data into this latent space, into the specific prior distribution of our choice. But we could also go ahead and construct this this latent space a little bit more progressively in terms of the amount of space, the amount of capacity we allow the model to use. So if we think back that the latent space represents the generative factors from which the data gets created or got created, then we can also think about occupying only some part of the space in the beginning, and as the further we go, we progressively increase the capacity in this latent space to accommodate new tasks without interfering necessarily with what we've already trained. And in the specific paper that I've linked on this slide, the way this is being done is rather intuitive. It's putting a constraint term on the KL divergence, which represents this representation capacity. So recall that the KL divergence controls how much we fit into this Gaussian in the latent space if we pick a Gaussian as a prior, whereas the expectation term on the top is the log likelihood for the reconstruction error, how good we're at reconstructing our inputs again. So we can put a C, it's called here a capacity term, that is subtracted from the KL divergence here, and initially maybe we can have this be rather large so that we penalize quite heavily, and as the further we go, we can allow it to occupy more capacity, to occupy more of the latent space to accommodate new tasks. Of course, there are many ways to actually think about this now. So I've illustrated two maybe intuitive versions where either you think about the distributions, you think about mixtures, you think about how many you can have and so on, or you think about this idea of how many paths you can have, how many activations activate in a large model where there are a lot of choices. But naturally, there are plenty of conceivable ideas, I'm sure with almost no limit, of how you could go about creating a very overparameterized model and later then figuring out subsets of representations or constrain it to subset of representations that belong to a particular task. You could do this through this activation overlap. Maybe you could induce some sort of slight parameter sparsity by having some regularization terms. You could do these ideas that we've just had on the previous two slides. You could also think of attention masks maybe on top. So rather than modifying some of the weights or some of the activations explicitly, you could think about putting like something like a gate on top and figuring out whether this should be on or off, like which subsets do you actually use in practice when you infer a task, and so on. But I think the important takeaway, at least for me personally, is that a lot of these methods work quite well in practice and are maybe sort of practical to implement and somewhat intuitive to think about. They're surely interesting, but also the question that kind of is open is, what if we don't actually want to always start with a very large overparameterized model? So what this is basically saying is that in order for this to work, in order to be able to identify these subpaths that then leave enough paths open for a new task, we'll need to also somehow gauge where to start. And surely we might be able to start with a very large model and then just assume this is practical. But sometimes, what if we don't want to do this? What if we're computationally constrained? What if we're memory constrained? Or what if we just simply care about the question, what's the adequate capacity for a particular task, so that we want to start with a model that's always just tailored to the task complexity at any point in time? So the perhaps, or at least to me, slightly more intuitive, but maybe, as we'll see, practically more difficult way to go about this is to think about the idea of preventing not only catastrophic forgetting, but also encoding new knowledge as creating a model that at one point in time is suitable for a particular task and trying to extend this model explicitly by adding parameters, by adding functions to it as we go over time. So as we figure out things get more complex or someone's told us to include a new task, we want to maybe also add parameters or respectively representational capacity in general. We can recall very briefly that this is a little bit inspired by maybe the transfer learning that we've seen in lecture 2. So there we've also already asked ourselves the question that if we have, for example, a deep neural network, which of the representations we already have are leverageable for the new task, which of the ones interfere maybe explicitly, and which of the ones that we already have maybe just don't give us any advantage. So you may recall from lecture 2 that we've seen these illustrations as on the left and the respective experimental results, where we thought about the idea of training on an initial task A, then either freezing or transferring some of the layer representations and figuring out whether that helps or hurts us in terms of training on the new task. Now we can ask ourselves basically in the simple form the same question, where we could start from the idea that we think of experts. So in the sense of we try to use the maximum amount of representations that are shareable as possible, but then afterwards we'll put intuitively an expert in terms of parameters on top. So it's illustrated on this left-hand diagram, where we could think about the problem of catastrophic forgetting, but also at the same time leveraging some of our knowledge in terms of a neural network by saying that we keep these initial layers and these are somehow shared. We'll maybe put a gating on top to figure out which of the features are really how important for some task. But then because we know that tasks are different and we don't really want to deal too much with this interference, especially if the tasks are too different and it becomes hard to consolidate it, we really put several expert heads on top. So you can see this illustrated here in this diagram, where in addition to like some representational backbone that's shared that produces a joint feature space, we would basically put really a lot of parameters or a lot of neural network layers on top that represents each and every single task individually after all. I think this is a very fair approach. It's somewhat of a solid and somewhat of what I call here a safe approach, in the sense of that if indeed the lower layer abstractions, as we've found out in the transfer learning lectures, are more general in principle, we'll also risk less in terms of overwriting our representations in terms of catastrophic forgetting by not sharing really like the deeper layers and putting experts on top. So in that sense, on the one hand, it's kind of maybe a stable approach. On the other hand, it's maybe also one where we don't necessarily leverage all the knowledge we could potentially share, with somewhat of a question mark. So I've put it as a maybe plus minus. It's not clear whether it's an advantage or not, because it kind of also depends on the tasks we want to take a look at. On the definite, at least in my opinion, but also shared by multiple scholars in the literature, on the definite negative side, there is potentially a difficulty, a challenge in figuring out which expert is supposed to be used. So even though you may have a gating mechanism on the bottom telling you that after you've surpassed your shared layers, your shared representations, you need to now start making a decision for a new example during prediction, which of the experts to infer. And of course, naturally, if you make a very wrong decision already at such an early stage, you'll now start calculating a lot of representations that may not necessarily have to do a lot with the task and arrive at a wrong conclusion as well. There are a lot of mechanisms to maybe get around this, but just potentially it is a challenge, it is a hurdle that needs to be overcome in order for this approach to be in fact feasible. So rather than maybe taking a look at this, I don't want to call it straightforward in that sense, because it still is an approach that is fair and challenging, but still, rather than this idea of putting experts on top and really not sharing everything, we could really go also to the extreme and ask ourselves, in this explicit perspective of adding capacity, of adding parameters, what if we really want to just add everywhere all the time? What if we really want to share everything? And I think, interestingly, there may be a connection here, or that it has been deliberated that there is a connection here in terms of what is happening in the brain, and it's called neurogenesis. So the inspiration here is that, again, I'm not a neuroscientist, but the idea is that in the human brain, or in general in brains of mammals, there are neurons that form over time, like new connections actually develop over time. So it's not just the question of updating the connections that we already have and reweighting them. It's also the question of really spawning new neurons, like spawning new connections in the first place, like randomly initialized new neurons, if you want to speak in neural network, artificial neural network language. Interestingly here, and we can read out the quote, is it says, after 2 decades of research, the neurosciences have come a long way from accepting that neural stem progenitor cells generate new neurons in the adult mammalian hippocampus to unraveling the functional role of adult-born neurons in cognition and emotional control. The finding that new neurons are born and become integrated into mature circuitry throughout life has challenged and subsequently reshaped our understanding of neural plasticity in the adult mammalian brain. So it's what I basically said in a different formulation, that it's rethinking this idea that it's a pure plasticity versus stability trade-off. So it's not just about, do we constrain some weights versus let others adapt? It's actually also a question of, are there new weights? Are there new connections that form in the first place? And to me, at least, the cool part about this is that in the first sentence, you can kind of get this feeling that it starts with after 2 decades of research. So in fact, if you look into the literature, it does in fact turn out that a lot of the older works, let's say, did not really support this hypothesis, in the sense, to the best of my understanding, that neurogenesis was primarily thought of something that happens only in very young and very early stages of life. And then as you grow up, it basically stops entirely. And at least nowadays, it seems to be the case that it's agreed upon that in certain brain areas, maybe not in all, but in certain brain areas, neurogenesis even continues towards the later stages of life, suggesting that the formation of new neurons, the addition of capacity over time, is perhaps a crucial mechanism to think about in terms of learning. We can again take a look at this maybe from an artificial neural network perspective in another old take and another quite intuitive perspective that's again 30 plus years old, but it's going to sketch the idea of how we could practically implement this quite well before we get to more complicated realizations. Initially, if we think of just a single neural network with like a single hidden layer, all we maybe think about is the dynamic creation of nodes in this layer. So we have just one layer where we can adapt the capacity. So what we can do is we can start with a small initial amount of parameters, and then we can start measuring our error during training. Now, the assumption is that this error during training is going to decay somewhat exponentially, as shown on the illustration in this graph on the top right here on this slide. So naturally, the intuition is that somehow in the beginning, as our parameters are randomly initialized and we have some loss function, this loss function gets optimized fairly quickly, in contrast to once we have started learning something, our representations maybe converge a little bit more, and the absolute sort of the relative decrease in terms of error from step to the next step decreases. It smooths out, it converges, it maybe asymptotically converges towards something. And so the question, or one of the central questions of when should we add a node, could perhaps be framed from just monitoring the error here and figuring out that when the error starts plateauing, we may want to add a new node into our neural network. So we may want to add new capacity, and then simply speaking, figure out whether this addition of a new neuron, of a new representational unit, does in fact now lead to a decrease in error, or whether it just continues to plateau in the same way and it made no difference. So we could take a look at a specific window here, as illustrated with this W on the x-axis and these double pointed arrows. we could take a look at the relative decrease in error on the y-axis in terms of these at minus a underscore t minus w quantities, and we could calculate something like this ratio. We could see whether this ratio becomes too small according to some user predefined threshold we've set, and then we could stop, or we could continue adding, or maybe even more ideally, we could stop as soon as we have reached some sort of cutoff performance on the with respect to the absolute error with respect to the y-axis, which is illustrated in the dashed line with the C on this slide. So the two questions that are basically asked here are, when do we add something? And the answer to this would be when the error starts to plateau. And the second question is, when would we stop? And the answer to this would be either because we've received no advantage after observing the error doesn't change when we add a unit, or the error has in fact changed, but up to a degree where the desirable amount of performance, the desirable amount of loss is finally reached. Naturally, this has a couple of assumptions, but I still think it's a pretty cool way to think about the problem. It's a very intuitive way to me to think about the problem. Just to, for completeness purposes, talk about the assumptions very briefly. If you think about what could go wrong here, then already the very first assumption that we've made is quite a big potential concern. So we've assumed that this error curve actually always decreases somewhat monotonically, and that it doesn't sort of do any weird behavior like fluctuations and so on. So it's really a monotonically decreasing function as illustrated on this slide. I think the fact that it's an exponentially decreasing function may be even less important than the fact that it's monotonically decreasing. So if you think about lecture 2, we talked briefly about stochastic gradient descent that we usually use nowadays all the time, where we could also make steps maybe in slightly wrong directions. You could imagine that this curve becomes somewhat wiggly. And so if we pick a window size that's maybe slightly off, where you don't pick a good window size where you could see a decrease, but just capture some of the noise, or maybe accidentally capture noise peak, you could potentially stop this algorithm way too early. So it is a problem that could be of concern. What I do find interesting, however, is not only the idea that it's simple and that it's intuitive to think about. I also find the idea interesting that in this specific literature example, the problems this has been investigated on are fairly straightforward to interpret. So what this means is that I think my YouTube may have skipped. I'm going to do a very small pause. If my YouTube is in fact working, it's okay, but I think it's lagging behind right now. Okay, thank you for the comment that you can see me on YouTube. I appreciate that. Then it's my panel that's causing errors, but that doesn't matter then, and I'll just continue speaking. I appreciate it. If I do in fact drop out, please drop a message in chat. So I'll continue where I left off. I think the interesting part is that the problems that have been investigated here are actually problems that have solutions that are in fact known in terms of how many units are required, at least in a hidden unit, in a single hidden layer example of the neural network. So the solutions here, for example, to the parity problem of an n-bit binary vector, so the question of whether it is in fact odd or even, like the odd or even question, is known to have a solution with n amount of units for an n-bit binary vector. And similarly, there are solutions for the other scenarios in here, with the exception of the binary addition task that's investigated here. But I do think that's a little bit interesting, because naturally, when we now think about the question of when to add parameters, of course, from a theoretical perspective, we would not only like to know, do we increase our performance, does our error drop, but we'd actually also like to know how close our final solution in terms of the parameters we have dynamically allocated over time corresponds to a somewhat reasonable solution, right? Like how far is it away from what we know we require to arrive at the solution? And so for that reason, I strongly or highly recommend just taking a look at this paper, because I find these graphs quite fascinating. And yeah, maybe we should get back to these a little bit in the future again as well. But what you can basically see for these problems here illustrated on the add3 example, you can see that on the y-axis, you'll have the absolute error displayed. On the x-axis, you'll have the amount of steps. The window is not illustrated here, but you can gauge it somehow visually. And you see the amount of units that have been, that are in the system at any point in time in this hidden layer, with these numbers and arrows on the top, with these dashed lines actually. So again, intuitively, every time the error plateaus, you can see on this specific example that it starts to plateau, and eventually we make the decision to add a unit. And as soon as we add the unit, it turns out that the error actually goes down quite a lot. And because we then again evaluate across the window for the with respect to the error we have started with before adding the unit, we continue because we see this drop has been rather massive. We can also see in step 4 that it would in principle be possible to mess this up if we were to pick the window size wrongly, because there is a little bit of noise in there. So it's something to take into account. But in this specific example, it actually works. And we continue decreasing by adding another unit, adding another unit, adding another unit. And in this case, actually to the point where we figure out that after we've started adding the 7th unit, we converge to a loss that's basically so close to 0 that our cutoff, our chosen desired we stop here criterion takes action. If you recall, the add3 was the one where we don't know how many units are actually required for a solution formally. Here it's 7, which somehow seems intuitive. In the paper, there are other plots as well for the parity problem, where, for example, for a parity 3 task, there is a solution that is found with only 4 units. So you could think that the, let's say, very simple take of approaching this idea in these easy examples works quite well. In general, there's actually a third question that we need to take care of, that we need to think about. So we've had the first of the second question be when to add and when to stop, but we haven't really asked ourselves yet how, or rather, what do we add specifically? So in this particular scenario, it's a fairly straightforward, it's a fairly easy question, because we've assumed we have a model that is a single neural network layer. So the only thing that we may want to add there are just the amount of parameters, the amount of units in that specific layer. But of course, in general, if you think of continual learning and tasks evolving over time, tasks changing, we may want to ask ourselves other questions that are not just about do we add one parameter or another. It's also about do we maybe want to add an entire neural network layer? Do we want to change the function? Do we want to add a completely different function? Do we want to change our inductive bias? Do we want to have multiple output heads on top or not, as we've talked about in the experts idea? And so all of these questions will depend a little bit also with respect to what are the tasks we try to model. So maybe if we go with a simple task as illustrated here, where we start with this like parity or addition problem that's mainly numerical data, but later maybe we want to go to images, maybe we want to go to text. This will quite crucially affect what we should add or what we should change in our models. So arguably maybe a single hidden layer neural network will empirically do quite well on this parity and addition task, but it's not going to do very well on a rather complicated language task or a rather complicated image task. So someone has in fact actually just asked this question, like, is this exclusive to a particular form of data like images, or is this are these ideas sort of agnostic? Can we use them for text files, etc.? And in fact, we do. But the question, of course, is what do we then need to add, or what are the knobs that we can add in the first place? And so in the next couple of slides, let's ask ourselves this question. So let's ask ourselves this question: what happens when we maybe change a little bit more than just having a static task and trying to find the right complexity to it? But what happens when we have some complexity for a task, but now add a new task and maybe want to change the complexity to also adapt and account for this task? The, again, slightly more complicated version of what we've just seen, but in a still, let's say, nicely intuitive version, is the idea that has been formulated later for deep neural networks in something that has been called progressive neural networks. So progressive neural networks really just suggested that there's something like a column, which is just a wording to mention that there is a neural network with a specific amount of hidden layers that points up to an output. And as we train a task, we can train this column, and then we could do something like we could freeze it and add another column, just like have another set of as many or maybe even more parameters that we allocate on the side that creates a second output. But in order to not just make this a second model that's completely disconnected and boring, we may want to have lateral connections that point to like this first column laterally to the second column. So the second column, the second hidden layer, for example, doesn't just take into account the first activation of this column, but it also takes into account the activations that were produced by the first column. But interestingly, as you can see here, it all just points like to the future. It doesn't ever point back. So if we think of this way to construct a progressive, like what is called here, progressive network to add capacity, it's very heavily, in fact, inspired by this transfer learning idea. So you can think of learning an initial task on output 1, then you freeze it. By freezing it, you know that you would not actually hurt your first task if you were to still infer that. But for the second task, you may want to sort of adopt some of the knowledge. So like in transfer learning, rather than maybe copying this and just keeping on training on it, you just let it go into your activations on the side, but keep on adding new parameters as well. So you can adaptively figure out whether the knowledge you already have is in fact helpful, or maybe even already solves the majority of the new task, or whether we may want to even discard and ignore this entirely and just build a second column from scratch. So it's somehow saying that we want to avoid forgetting where possible by mainly freezing or largely constraining, but also at the same time allowing as much transfer to new tasks as possible by letting our connections choose, in that sense, how much to transfer. Interestingly, that also means that there is fairly little advantage in this in terms of retrospectively improving our tasks. So because connections only go forward, if we figure out that we could learn some representations based on the data of our second task that potentially would help our first task quite a lot, we would not really gain any benefits if we really chose to freeze weights. So again, we might want to, let's say, partially freeze the weights or just give them a much lower learning rate so we have a little bit of forgetting, but not too much. But basically, if we think of this progressive networks idea as really just adding a whole new complete chunk of parameters at every layer of a model, then we can think of the evaluation in pretty much the exact same way as we've seen in lecture 2 of the transfer learning scenario. So we could think of all these different baselines of just having parameters only for the target task, having parameters where part of the source task is copied and frozen and only a little bit for the target is trained on top, or we copy but then adapt with a lower learning rate. And we could transfer precisely these questions into a setup where we don't only have like one of these forward columns, but multiple on the side with these lateral connections. And of course, then we can ask the same questions again. We can ask ourselves the question, do the frozen weights from source tasks, do they help? Like, do these lateral connections then form in order to accelerate the learning of the new task? Do they not? Are they useless? And in fact, we could do this in a quite nice visual form as illustrated on this top left panel here in this plot with the subscript A, or these two plots with the subscript A. So you could see here in terms of the coloring is you can see the blue indicating that it's very sensitive. So it has like a high transfer score, versus if it's basically white, it doesn't really transfer at all. It's not really that helpful. So in that sense, you could see that in some tasks, you have clear like blue activation patterns across tasks, whereas in others you don't really. So let's take a look at a specific example on the very left, where you have a sequence of first sequest, then pong, and then star gunner. And you could see that, in fact, in the three columns on the x-axis, with the layers of convolution 1, 2, 3, and the last fully connected layers, it does in fact seem to be the case that in order to play star gunner, you do leverage the representations in the convolutions from sequest and pong quite heavily, in contrast to the white, basically rather obsolete, newly added representations that you may not really require to learn in order to now play star gunner. But you can also on the very on the opposite side have the exact opposite pattern where maybe you don't really transfer at all, right? Like maybe you only train new representations for new tasks, and all of the stuff you've previously trained, you ignore it because it's not really helpful. Of course, you could also see this quantitatively in the right-hand plot illustrated in B, or the pair of plots, where you could now rather intuitively see that in contrast to these transfer learning baselines, where you just have the single column where you don't add new parameters, but you try to freeze or adapt the ones you already have, the progressive addition does in fact give you a lot of benefit. It either gives you a benefit in the left panel in terms of just being overall a lot better if you in fact require new representations to be learned, or it could just be that if you have, for example, the right-hand plot, that it simply accelerates the training. So you can have various benefits, but in any case, it's another sort of intuitive way to think about it. But of course, we've kind of sidelined the question of what to add and how much to add by just saying we always add like big chunks, we avoid catastrophic forgetting but not touching old representations, we just have these lateral connections. So I think a very good interlude or a very good question to ask at this point is really, and I'm saying this like slightly provocatively, but with the best of intentions, as you'll see in a slide or two, but I want to just provocatively ask the question, aren't some of these solutions obvious? Again, without trying to discredit any of the authors of the previous slides. And I'm saying this because you could somehow ask yourself, oh man, anyone could have come up with this. In the sense of really, anyone could have thought of the idea of, sure, I take a neural network, I know all of this transfer learning stuff sometimes works, I just put another neural network on the side, laterally connected, I transfer some of the representations, other I don't. It seems so trivial. Maybe some of you will say it doesn't seem trivial, but maybe someone might say it's trivial. I think an important fact is that two of the papers I've just presented, which I highly cherish, they are very well cited, but somehow they have also never been published in the sense of they're sitting on the archive, they're archival papers, without having seemingly made it into like official conference proceedings, to the best of my knowledge. If you are aware that they have indeed been published, please, of course, correct this in the comments. But anyway, I don't even think this is a problem because the ideas are nice, they're intuitive, and I think the quote that has been made in one of these papers is quite essential in answering the question of, aren't some of these solutions obvious? Because maybe it's not the right question here. There's also a question which is illustrated in this quote, that while many of the individual ingredients used in progressiveness can be found in the literature, their combination and use in solving complex sequences of tasks is novel. So it's always a question, I think, of things can be very intuitive in retrospect, but unless someone has done and shown it to you, has it really been that obvious? So I just want to put this out because I think when you're listening to this presentation, maybe you're partially not very surprised. Maybe you are, I don't know, but I just want to put this out there as a small sort of reminder, as a small interlude. And in particular, I want to use this as a transition to really draw attention to the fact that when moving from this implicit perspective of like having a very large model and just trying to do these regularization questions, these figuring out subset questions, to really these questions of adding, removing, like modifying capacity on the fly, there are a lot of questions that are in themselves quite challenging, like what to start with, when to add or remove, what to remove or add, how much at the time, when to stop. But also, I think it's very crucially challenging to connect these questions and do them all at the same time in concrete algorithms and applications. So I think that's very important to mention in this lecture, that although individual elements may seem more intuitive than others, or rather intuitive, it's a field like these dynamic architectures, especially if you want to maybe do it formally, that's, in my opinion, brutally challenging to solve. Now, I want to end this lecture with a couple of, with another example and a little bit of a discussion as well, where again, as always, it's not just a picture of I can do either, I can do or. So of course, I don't have to just regularize. I don't have to do what progressive nets do and just add a chunk on the side and have lateral connections. I can, in fact, do both at the same time maybe, or do combinations of things we've already seen, as we should be quite familiar with now. So on this specific example, you just see the idea of elastic weight consolidation. You see the idea of progressive networks. We've had both. So elastic weight consolidation does not have an expansion component. It just tries to regularize important parameters and figure out these subsets. Progressive networks does what we've just seen. It adds capacity on the side. It just increases like a lot of parameters at a time. And maybe there are combinations of these. One of the ones that has recently been proposed is called DEN, or just short for dynamically expandable neural networks. And it's an approach that, in fact, has 3 steps that are really a combination of a lot of the concepts we've so far seen in the course. The first one would be you start with maybe not an overparameterized network, but something which, as a rule of thumb, you think fits the capacity of the problem. This in itself is already quite a challenging question, especially for complex problems and deep neural networks. But so what is advocated is start with this this sort of model and pick one of the selective training strategies. So where you basically try to selectively train some of the units to be particularly responsive to a task. What you'll then do is you'll figure out if through this training you reach a certain loss, or whether you cannot surpass this loss. So the intuition is that if you do in fact reach the loss you think is adequate, is desirable for this task, that means you may not currently need to add units at this point in time or add layers. If not, if you actually cannot reach this amount of loss, this performance or accuracy, whatever measure you have that you like, you may want to do what progressive neural networks do and just add capacity on the side. Now you can add this to sideline the question of how much you want to add. You can maybe add a lot at one point in time. And rather than figuring out how much is reasonable, you can first add it and then repeat this process again of potentially being selective to only a few parameters and maybe even pruning away some of them again, like killing them, completely deleting these units again. You could also maybe then split units, you could duplicate units, and so on. So it's just an example to illustrate to you that naturally there are various combinations of ways we can approach this idea now. Some are maybe formally more approachable than others, but maybe some are empirically more approachable. And so rather than solving each and every individual question, like when do we add, how do we add, how much do we add, we can sideline some of these questions, but by going with some heuristic approaches, like adding a lot at a time, and if we figure out we've added too much, maybe we remove some of it again. Empirically speaking, this may work out quite well. And so it also brings us to the point that the efficiency, but maybe not only the efficiency, but the efficacy of these approaches may be hard to interpret. And this is, first of all, because there are so many different ways to approach this. So unless we really measure a lot of different things, like amount of parameters at any point of time versus losses versus compute overheads, etc., we'll talk about this in detail in the next lecture on evaluation. It may be just hard to interpret these models, but also specifically before talking about the more broad evaluation, something I want to draw attention to in the remainder of the lecture today is that whatever we've talked about so far is very often framed, especially in scientific papers, as measures to combat catastrophic forgetting. So sure, progressive networks have been framed also as knowledge transfer, but dynamically expandable networks, for example, they have been framed as something to avoid catastrophic forgetting. And either way, whether it's forgetting or transfer, it's all about like forward or backward knowledge transfer. What we do need to keep in mind though, and that's why I've started this in the beginning of the lecture, is that adequate capacity, like finding suitable capacity, is not just a question of forgetting. It's not just a question of knowledge transfer. It's actually a question of finding the right and suitable amount of capacity for a particular problem. So if you think back very briefly on this this parity problem, this addition problem on this single neural network with one hidden layer, you could see that even on just one task, there's a particular solution that converges quite well, that solves this task quite well. And independently of whether we're sitting in a continual learning setting or not, we may want to think about this. But particularly in any continual learning scenarios where something along the lines of data changes over time, this is an effect we need to consider as well, rather than just maybe measuring how much do we forget, how much do we not forget. And so I want to give a very intuitive example to think about this by taking a look at the dynamic or modular architectures from an active learning perspective. So the reason why we have not talked about dynamic or modular architectures right away in lecture number 4, when we talked about catastrophic forgetting and this picture with these different perspectives of how to think about this, the reason is that I first wanted to go into active learning in order to look back to this example now to really make it clear that dynamic and modular architectures are more than just a method to avoid catastrophic forgetting. And so the proposal that has been made in a specific incremental architecture approach that I'm showing on this slide is quite simple, which is why I've chosen it. It's simple, but it's great at the same time, because all it's really doing is it's formulating the architecture choice from a very greedy perspective. So what it's doing is at any point in time of an active learning query, so keep in mind that active learning was this idea that we've talked about last time where we always query from like a big pool or a stream to figure out which data elements do we include to improve our model. And so we can have a greedy choice of 3 options that we could consider at any point in time when we do a query. The first one would be the very intuitive choice. We assume that whatever architecture, whatever model we've already started with is adequate. So we just stick with the present architecture, the present amount of parameters. The other 2 intuitive versions, at least for a neural network, are one where we say the amount of layers is great and the choice of layers is okay. We only want to add more parameters. We want to add more representational capacity. Let's pick another architecture of the same style, but add more units in terms of width, just add more capacity on each layer. And the third one would be the, let's say, orthogonal question to this, where we say, maybe let's not add parameters in terms of width, let's add parameters in terms of depth. And so what you would do is at any point in time of query, you would actually really train all of these 3 for a while and figure out greedily which one performs best and take that as a choice to continue on before you make the next query and start the same question again. You could see this illustrated on this number of blocks versus number of stacks, which is the author's definition for number of layers and sort of the width of the layer, where you could see this illustrated here on a simple matrix in terms of I and j indices. You'd start with something like a 1 layer, 1 unit of number of width. So it's not just 1 parameter, but it's like discretized in 1 is something like 16 or 32 or so parameters. So you add in chunks so that it's sort of more computationally efficient. But you would start with like 1 layer or one block of layers, and then you'd increase either the amount of layers to the one axis or the number of width. So obviously, every time you introduce a new layer, you would double the amount of parameters, for example, when you go from one layer to two layers, versus if you just increase the width, you'll actually just increase the amount of parameters on that axis. You could see, so you just greedily go through this, you eventually arrive at a larger model, and then you can try to see what happens when you put this into an active learner. So on this diagram on the left-hand side, you can see an active learner in practice. It's on one of the popular benchmark problems. It doesn't actually so much matter which one it is here, so I've removed it. And I've actually also removed various other information, such as what the curves mean, because I do believe it's a very good idea to, at this point, make you think about what these curves could be, depending on what we've just said so far in the lecture. So naturally, one of these curves is going to be this incremental architecture approach that we've had on this slide, where at each point in time, you greedily make a choice whether or not to expand the architecture. But the other two lines also represent something different. And the question, of course, for you would be, what would you intuitively think, first of all, which of these lines is the incremental architecture approach? And what do the other two lines represent? Now, just recall that it's an active learning plot. The query, the acquisition function here is actually the softmax response. So we just query according to the data that we include next is the one that has the smallest softmax response. So it's the least likely, the least confident. Although we've said that it's not necessarily the best measure, for the purposes in this diagram, it doesn't matter. And so we can see on the x-axis, we start querying data points and include them into a training. And on the y-axis, we see the test accuracy in a classification problem at any point in time. And so pause the video maybe for a moment if you're watching this offline and think about what these three curves could really represent and which one is which. Okay, if you've done that, I can resolve this for you and just really do these like practical exercises because I think it's helpful of how to think about it. Now, funny enough, the last time I did this lecture, just like recently on in person, someone has said the black line is obviously the incremental architecture approach. And when I asked why, the person responded with, well, it's a publication, so naturally the idea that the authors have published must have been the best. I think it's a very valid approach. I just wanted to point this out because I think it's quite a nice idea that also maybe illustrates the fact that we have a bias in our publication system. But jokes and sidelines aside, the black line is indeed the architecture approach where you incrementally decide whether to expand or not. Before we say why it is the black line, let's maybe take a look at the other two curves. So you may have intuitively already thought that one of them will be a static baseline. In fact, both of them are actually static baselines, meaning both of them do not represent approaches where the capacity, where the amount of parameters or the amount of layers is modified in any way at all during the course of training. But what they actually represent is the blue line is a fixed neural network, which is rather large. Here, a popular residual neural network that's very popular when you look at like public repositories and GitHub and so on. The red line, on the contrast, is actually the fixed small architecture that the black line starts out with. So it's not surprising in the sense of that they do start out with a very similar performance. But you can also see that apparently at the point where they start diverging, the black line must have made a choice to expand the architecture, given the fact that they no longer coincide. Otherwise, if they had the same architecture, they would have been the same. And interestingly, I think we can really observe what we've seen on the slide where we have the amount of data points on the x-axis versus the performance, the optimal capacity on the y-axis. We can really see this manifested in this plot here. So the red line, it starts with a small scale problem, with a small data problem, with a small architecture, which fits quite nicely. So it has a good accuracy at the start. But eventually, as you go on and you keep on adding too many data points for too little parameters to capture all the complexity, you start seeing that the red line is the overall worst in the end. In contrast, on the blue line, what you can see is that it starts out quite badly. It takes a really long time to actually get up to speed, get up to accuracy, because initially when you have very few labeled data points, you have quite a big mismatch with respect to this optimal capacity versus data complexity curve. And so you're struggling to basically perform as well as the other architectures here. And it takes a bunch of data points and some time of training before it actually outperforms the red line at around here, I think 15,000 or so data points for this specific example. The reason why the black line is the best of both worlds is because you start small when you have something that's lower in terms of complexity, where you have less data points available, but you make the greedy choice here to adapt the architecture to expand it when you require this additional complexity to capture the task fully. So that's why you have the best performance at any point in time. But I think then this plot also tells you that it's not just about catastrophic forgetting. It's just about not just about, but it's also about accuracy and losses at any point in time, and just trying to match the complexity of a model to the complexity of your tasks, which play a very crucial role, which in my opinion is at least as important as the question of avoiding catastrophic forgetting. So in that sense, when we talk about evaluation next week, we'll maybe think about what it actually means when we see these dynamic architecture approaches being measured in a single plot where all that is depicted is catastrophic forgetting, because it's not very clear for us how this relates to the curve we're just seeing on this slide. Naturally, the curve, or interestingly and importantly, the curve I've just shown you is only a subset of various such plots in the paper this is presented in, where you can again see the same style of patterns appearing, not only if you choose an acquisition function for the active learning part based on softmax responses, but you also see this uncertainty approximation with Monte Carlo dropout, which we've briefly discussed. You also see the same thing when we talk about course sets as a mean to active learning. But very importantly, you'll always see like very similar patterns here, that it's just extremely important to have an architecture that matches the complexity of your task, that adapts to the complexity of the task, if we're in a continuous learning process of whatever form that adapts the data we see. So this may be continual learning in the sense of adding tasks over time, but it may also just be active learning in terms of growing our data set over time on a single task where the distribution just gets more complex. And so as always, this is maybe already decently complicated, but it may get even more complicated than this, which is why dynamic and modular architectures are something that's extremely interesting, but in my opinion, something that's potentially also somewhat hard to think about. And the example I want to show off to wrap up the lecture for today on the dynamic and modular architecture side is the choice of model and scale and how it's combined. It's based on an extremely recent publication that literally just came out like 2 months ago, where the thing that's been investigated is for two tasks, so task A and B, just here illustrated on the X and Y axes of these first two plots. It is investigated how much basically the model forgets depending on the size of the model. So it's not about the specific algorithm we put into place about how to prevent catastrophic forgetting. It's really about, let's not care about any of this. Let's not put any algorithm at all and see which methods sort of forget more, which methods forget less. Models, not methods. Which models forget less and which forget more, depending on their size. And so in the legend, you can see, first of all, that there are two types of models investigated here: residual neural networks. For those of you who are not familiar with residual neural networks, it's basically a fairly sequential neural network with a lot of layers that has skip connections that basically bypass some of the layers. So it jumps from, for example, from layer 1 to layer 3 instead of going through layer 2 exclusively. And in contrary to this, vision transformers. So visual transformers are a fairly new model where, in addition to the like standard operations you have in a neural network, you'll also have attention operations included. And so interestingly, on this legend, you can see the amount of parameters in these models. And then evidently in the plot, you can see that as the amount of parameters grows, so does the amount of forgetting shrink. So in that sense, you're going further towards the top right corner of these plots, suggesting that the choice of model and the scale of the model affects how much you forget, in the sense of you could, in fact, maybe go from this implicit perspective that we've talked about if you go really extreme and go with an extremely large model. So apparently, if you choose a residual network or a visual transformer with 80 million parameters for this particular problem, you just have so many parameters available that you can always capture one task, and you'll not use the entire representations in terms of overlapping them all, that you'll still potentially have enough representations to encode the new task in addition. So it's like taking this implicit way of thinking about architectures and modular architectures to somewhat of an extreme, maybe giving you an idea of why very, very large scale language models, very large scale transformer models are currently being hyped so much. It's somewhat of an interesting take, but it also shows, again, maybe my opinion, but quite provocatively, that we don't really have too much of an idea like when this breaks down, when it works, and so on. Especially this representation overlap idea in deep learning is largely unsolved. It's a very challenging thing to think about. I think this becomes even more clear when we not only take a look at the top two left plots that are in color, but if we take a look at the curves on the top right, where you have the title for the plot named error scaling. So what you see here is the best average error on the y-axis versus the amount of model parameters on the x-axis. And you see a couple of points in the plot, but you also see an interpolation between, or a linear fit between these points. Once for the visual transformer in the filled black dots with the dashed line, and once for the residual neural networks with the circular non-filled markers. And so here you can very clearly see that even at the same amount of parameters, the visual transformer at any point in time seems to suffer from a lot less forgetting overall than the residual network. It just overall performs a lot better in these scenarios. And so we can ask ourselves why this is the case, that not only the amount of parameters, of course, matters, but also the choice of model, which is something that we haven't talked about so far today, where although we've talked about how do we add parameters, how do we add maybe layers, so how do we change the representational capacity, we have not so far questioned the role of the functions we put into the model themselves. And so in this example, the red plot here is again the same that we've seen on the previous slide. It's quite interesting to see that this choice of model can have a very dramatic effect on the forgetting amount that we have. And the left plot rather intuitively shows why this is the case. So what you see here is the amount of overlap for classes measured with respect to the representations for different model parameters. And the argument that's being made here, first of all, is that the visual transformer on the very bottom seems to have a lot less overlap in terms of its representations. So representations are a lot more orthogonal with respect to another, in contrast to the residual neural network that's trained from scratch at the very top, which has a lot of overlap, close to 90%. So in that sense, it's like saying that apparently the attention mechanisms that we put into the visual transformer and the way it's composed somehow implicitly has a little bit, maybe even explicitly, because we did put in attention, but has put in a mechanism that goes a little bit towards this like activation sharpening idea to prevent all of the activations from overlapping. So there still is overlap, but we'll have sufficient distinction such that when we train like a downstream task, we don't suffer immediately from catastrophic forgetting phenomena and suffer from forgetting more amicably. In addition, as a second thing that is that we can observe on this plot is actually that for the residual network, there seems to be quite a large difference with respect to whether we've trained the residual neural networks from scratch or whether we have pre-trained them. So the pre-training here has been done on a very large data set. But interestingly, for the very large data set, it's not about the question, do you perform better? Because that's maybe if the data set is very large and the data sets that are investigated are a subset of this is quite evident. It's actually showing that when you then train the overlap in terms of the representations at the same amount of capacity, at the same amount of model parameters, is actually also lessened. Again, intuitively, this would be resulting in less catastrophic forgetting. So in that sense, what we've learned is that we can maybe sideline the question of explicitly adding parameters and thinking about this quite comprehensively from the perspective of just going the reverse route, going with extremely large models. But we have also learned that the model choice itself may play a very big role. So there's still a lot to be done in figuring out which models are more amenable to figuring out solutions for continual learning than others. And with that said, there are actually other ways to think about suitable architecture configurations in general, not just in terms of the implicit perspective, as I've called it, and the explicit perspective, but just approaching this from a completely different perspective, which is very often referred to as meta-learning. And so meta-learning is frequently called learning to learn. And we could think about this for neural architectures, as we've discussed today, in the sense of the loop, for example, that's shown on the right-hand illustration. So something we could do is we could put a machine learner on top of the machine learner, essentially, which has like an optimization problem on top of what we're already optimizing. So the inner optimization problem is in this blue box, which is we train a neural network architecture and we get some accuracy, some loss value with it. Now we could record this architecture, this specific configuration, together with this loss function, and basically sample a bunch of random architectures and create a data set with this. And then on this data set of how well a specific architecture configuration performs in a specific task, we could put another machine learning optimizer on top that now tries to learn which building blocks are basically important for which sort of tasks, for which sort of applications, and then try to learn how to generate these automatically so that when we see a new task, the meta learner, this like outer optimizer, immediately tells us, oh, we'll need an architecture that looks like this and that in order to be successful on the task we're now seeing. And naturally, if we then think of this as like two optimization problems in a somewhat computational heavy way, we're no longer just restricted to finding a suitable model variant, but we could also figure out how to maybe adapt and learn a loss function itself, adapt and learn an optimizer itself. And it's something we'll talk about in a later lecture. If we're a little bit lucky, it will be a guest lecture where we'll revisit this meta-learning perspective explicitly and talk about how meta-learning in general could connect to the ideas of continual learning. So with that, I'm at the end of today's lecture. And before we end the stream and end the video recording, given that we've now passed 6 weeks and it's halftime, I wanted to have 3 small slides to have a little bit of a recap and a little bit of an outlook also, so that you can consolidate what we've already seen, put it into a perspective, and also get a little bit of a perspective of what we're still about to see in the future. So what have we seen so far? We've talked a lot about similar topics in the sense of we've had a motivation and a rough course overview, but after that, for a long time, it's been about transfer of knowledge and retention of knowledge. So we first talked about transfer learning from source to target tasks. We've then talked about catastrophic forgetting in 2 lectures, from the optimization and regularization side first, and then also from the data perspective in terms of rehearsal and pseudo-rehearsal with generative models. We've then had these, let's say, reverse perspective of not asking ourselves like what to forget if we have new data, but actually asking ourselves, what is the new data? How can we pick the new data? And just today, we've essentially finished up what is typically referred to in the literature as like the third way to think about catastrophic forgetting, with hopefully enough of a perspective from my side to make you understand that this is more than just a method to talk about forgetting, in the sense of that dynamic and modular architectures are just a fascinating concept to think about in general in machine learning. And it is, in fact, something that we should always think about for whatever task we consider, independently of whether it's continual or not continual learning. So in that sense, I think we've gained a good initial overview of not only the ways to think about various continual learning questions and varied knowledge transfer questions, but also have visited some techniques. So in that sense, if you now read this paper and you see this like survey and you go through the like paradigms of people who present surveys of continual learning, you're hopefully good enough or at a point where you would have sufficient understanding to read these surveys and understand what is truly happening, at least in the sense of getting the ideas of what perspectives do people come from, so that when you later look into the individual algorithms of how they are formulated, you can understand the motivation, you can understand why specific choices may have been made and what the goal of this is. So naturally, we've covered now these actual 4 perspectives on here, A, B, C, D, but surely there is a lot that is still missing that we need to still cover, and it's illustrated on this slide here. Now, I've already mentioned earlier in the lecture that the first thing we'll talk about next is evaluation. You may have noticed that up to now, we've talked fairly little about evaluation in terms of what do we actually want to evaluate, what are our evaluation desiderata, what are the assumptions. We've always sprinkled in a little bit of this flavor, but we've never really questioned if what we see on specific plots is actually the thing we would like to measure in practice. So if we think back on today's lecture, I've already shown you an active learning plot where it was visible that as we scale the data, we may need to scale the architecture as well in terms of the performance. Then it's already apparent that if we just show an incremental architecture approach that modifies capacity over time, and the only thing we show on the y-axis is catastrophic forgetting, that this may be somewhat misleading because it's discounting one of the important factors. And because it's so hard to actually think about evaluation, we've put it off in a sense to lecture 7 to first get some of the ideas, get some of the algorithms, so that next week we can now start to think about not only about the question of like, what is it we actually want to measure? Spoiler alert, I don't think we're at the stage yet where there is any sort of consensus of what it is we actually want to measure. And thus, interestingly, of course, why is it so challenging? Why is this a topic that we'll need to discuss and devote an entire lecture to? And after we've talked a little bit about this evaluation part, we can then transition to what I would personally refer to some of the, let's say, less clear topics, less clear in the sense of that will increasingly have less of a solution of how to approach this that's somewhat unique. So in the sense of there's not really that much of a consensus of this is like the way to think about it, this is, or not even this is the 3 ways to think about it, but really just exploring the open space, starting with really the idea, speaking of open, what will happen when we really encounter unknown data. And what is meant by that is that so far, whatever we've seen, even on these active learning plots, we've always had something that's unknown that we actually know about in front. So we do actually know when we have a plot where on the x-axis it's the entirety of the data set, that whatever is in our pool does in fact belong to this task. So similarly, when we put a continual learning problem as playing Pong first and then a different Atari game, we know upfront that whatever is unknown to our learner is in fact a known Atari task. We've never so far considered the question of what if whatever data we encounter next, or whatever data we could query actively next, is something we have no clue about in terms of what it even represents. And so this is what we'll talk about after the evaluation lecture, because it's going to become increasingly harder to think about what it actually is we want to measure. We'll then finish off this cycle with algorithms in learning curricula and other interesting effects. So a curriculum is the effect of like ordering task data and all the interesting patterns we can see there. and we'll talk a little bit to finish off the entire course about the role of software and hardware, primarily because I think a lot of the research is driven by software and hardware, and we'll talk about this, followed by abstracting away from this complete perspective to frame machine learning from a perspective of meta learning, as we've just alluded to, in the sense of what if we don't actually try to solve the machine learning task, but try to solve the machine learning through another machine learning task in a very staged, abstracted way, which will lead us to transition to research frontiers and finish up the course then overall. So with that, I hope you're now at a stage where you have some initial ideas about how continual learning is sometimes framed. You've already encountered some examples of how active learning, for example, is one way to think about continuous learning that fits into this quite well. We've talked about knowledge transfer. You've seen some techniques. So I hope that the initial overview is sensible to you, that you are getting a feeling of really getting the grip on this topic, and that we can really tighten this grip with future lectures to give you a more comprehensive view of how to think about this entire field as a whole. And with that, I'm done with today's lecture. If you have any remaining questions, feel free to ask them in text now. Otherwise, otherwise we're finished for today, and I appreciate all of you for coming here and listening to not only this lecture, but also the past 6 lectures. And I hope that you'll join for the second half that's still to come. Okay, I think I've waited long enough for the YouTube delay to have taken its place. If there are no further questions, again, much appreciation. And yes, so I see the thank you note in chat, so you've had the chance to ask questions. So I also wish everyone a nice evening and see you next time.